Hi everyone, welcome back to Math 112. This is Scott. Let's get started. Today we'll be talking about section 5.3. Last section we introduced the trigonometric functions, and in this section we'll discuss their properties. Properties of the trigonometric functions. So, by trigonometric functions, we mean, of course, our six friends: sine, cosine, tangent, cosecant, secant, and cotangent. Alright, first, let's talk about a property called periodicity. So, since the trigonometric functions all have to do with the coordinates of points on circles, as we go around and around the circle, obviously things get into a little bit of a loop. And that's what periodicity refers to. So a function is periodic with period p greater than 0 if f of t is equal to f of t plus p. For all t. Now basically what this means is that the function repeats every p units. Repeats its output values every p units. Alright, so here's a fact. And in order to inspire the fact, we'll just meditate for a second on the circle. So if we are talking about the unit circle, and we are talking about, let's just call this a circle radius 1, so the unit circle. So if this is the situation, and we are moving around the circle in the standard trigonometric orientation, and we look at just the y values, that will give us the sines. We will end up repeating ourselves as soon as we have completed the circle. Once you go around, and then you're back where you started, everything will repeat all over again. So all of the trigonometric functions that involve either just the x or just the y will repeat with period 1 full rotation. So the functions sine, cosine, and then also their reciprocals, cosecant and secant, are all periodic. With period 2 pi. In other words, one full rotation. Now, if you happen to be measuring in degrees, which we'll do less and less frequently as this course progresses, but if you happen to be measuring in degrees, then it would be 360 degrees. Now, this makes complete sense, I think, if we just imagine a clock. Clock's minute hands are in the same position at every time within each hour, and so it makes total sense that this would be periodic with period 2 pi, or 360 degrees. Now, that is not all of our trigonometric functions. The tangent and the cotangent, however, those are also, although they're also periodic, they're not periodic with the same period. The functions tangent and cotangent are periodic with period pi, or, oops, no, 260, 180 degrees. And the reason for that, so that may at first seem a little odd to you. All the other functions repeat themselves every full circle. So why would these ones repeat themselves every half circle? Well, if you think about what a half circle would mean is, it would mean going from here to here, so diametrically opposed points. By the way, the word diametrically means they are opposed by one diameter. So they are on opposite sides of a diameter. So whenever you have these points right here, they actually lie on a ray that has the same slope, like going in the quadrant 1 or in quadrant 3. And what that means is the ratio of y over x or x over y, whether we're talking about tangent or cotangent, will be the same. So the ratio y over x, i.e. the slope, is the same for these two line segments. So whether we're talking about the one that's in quadrant 1 or the one that's in quadrant 3, they'll be the same slope, and the same is true of points that are diametrically opposed in quadrants 2 and 4. So that means that the function values will start repeating themselves for our tangent and cotangent, not every 2 pi, but actually every half of a rotation, so every pi, or 180 degrees. So, using this, when confronted with unfamiliar angles, what we can do is add or subtract any multiple of the period until we create a version of the angle that is within our storehouse of knowledge. So we can add or subtract any multiple of the period of the particular function in question to produce a better known angle. So, as an example, so to start relatively simply here, let's go with something that's in degrees. We'll typically often start with degrees just to get our feet wet because degrees are just a little bit more within our usual competence level. We understand degrees from a lifetime of exposure in a way that we don't quite understand radians, which we just learned about a week ago. So here, what we're going to do is use the periodicity So periodicity is in periodicness of the trigonometric functions to evaluate. To evaluate each expression exactly. And what exactly means is no calculator. So no calculator. The code word exactly usually means that. Where calculators are involved, they start producing decimals, and so we have gone from the world of the exact into the world of the approximate as soon as you start rounding things, even if you round it to like 12 decimal places. Alright, let's start here with something like the cosine of 420 degrees. Now, technically, we already know how to do this. We just haven't formalized it in this exact way, as in turning it into a matter of the periodic nature. So, cosine of 420 degrees. Actually, here, let me just. So, 420 is equal to. We can see that that is more than 360. And actually, so the best way to write this, how about this? We'll just subtract the 360 from it and see what we get. And 420 minus 360 is equal to 60 degrees. And so what that means is that if this is truly a periodic function, adding or subtracting 360 degrees won't change its value. So that means the cosine of 420 degrees is the same as the cosine of 60 degrees. And 60 degrees, that's one of our familiar angles. That's the one that is in quadrant 1. It's up a little bit on the higher side, which means its x value is going to be a little bit on the lower side, which means the x value will be 1/2, and the y value will be root 3 over 2. This is one of the angles that we've studied, and so this we know to equal 1/2. All right. Now, what if we were to talk about something like the sine of 390 degrees? Well, again, we are outside of our bounds of more comfortable angles, so we can just subtract 360 or add 360, as the case may be, until we are left in a more familiar footing. So this is equal to just 30 degrees, which means that the sine of 390 degrees happens to equal the same thing as the sine of just 30 degrees. And again, that's an angle that we have some experience with from the unit circle. That's the one that's down here. It's a little bit on the lower side. So that means that the x is the bigger value, so that's root 3 over 2. And the y is the smaller value, that would be the 1/2. So that'll equal, again, 1/2. So once again, we got an answer that was a half, and it comes down to cutting the angle that we're given down to size until it matches one of the known angles from the unit circle that we have studied so intensely. Now, what if it's a different angle, or a different function? What if it's secant? How do we deal with that? So let's go secant 540. And again, just add or subtract 360 until we end up back in a more familiar territory. Now, if this were tangent or cotangent, we would be adding or subtracting 180 until we ended up where we wanted to be. But what's 540 minus 360? So it looks like if we subtract those, it's going to be 180. So secant of 540 is the same as the secant of 180. I just wrote the parentheses randomly there. No reason. Okay, so let's think about that. Well, 180 degrees, that would be over here, that point. So this is a unit circle, so that's going to be a -1 for the x, and it's going to be a 0 for the y. And so the secant is equal to -1, or sorry, 1 over -1, I should say, which is just -1. All right. Now, we already calculated the cosine of 420. Let's just now think about, let's say, the cosecant of 420. And then after this, we'll switch over to radians and try some in that form. So the cosecant of 420, again, we just think, all right, what is 420 minus 360? We just add or subtract 360 until we were within our usual format. So again, this is equal to 60 degrees, just like it did before. Now, once again, we can just quickly jot down what point it would be on the unit circle. And we can see that the x value here would be 1/2, and the y value would be root 3 over 2. And so that then immediately tells us that the cosecant of 420, which is the same thing, 420 degrees, the same thing as the cosecant of 60 degrees, will have to equal, and it's the reciprocal of the y. And of course, we by now, after the last section, have learned that we have to rationalize these whenever we can. So what's that equal? So root 3 becomes root 9, which is 3. And so we get 2 root 3 over 3. All right. So that's how it works with degrees. You just add or subtract 360 until you are at a more familiar angle, whenever it's one of these functions. Now, what if we're talking about something that's in radians, or we're talking about something that's tangent? Actually, I guess we better do a tangent first still while we're in degrees here. So that was D, so part E, last one. Let's do the tangent of 390 degrees. All right. 390 degrees. Well, if we subtract 180, that's still going to leave us at 210. And so we can actually subtract 180 again. And that'll get us again to 30 degrees. Our old bread and butter, 30 degrees. 30, 60, 45, these are our main angles that we're going to be focusing most of our attention on. And so, and again, remember, tangent and cotangent, they have a period of 180. So that's an important fact when it comes to crunching the numbers on them. So again, we're talking about 30 degrees, so that's going to be a big X and a small y, so that means root 3 over 2, 1/2. And then the tangent of 390 degrees, which is equal to the tangent of 30 degrees, is going to equal the 1 over the other, so the y over the x. So that's 1/2 over root 3 over 2. And again, this is a situation where we can just multiply the top and bottom by 2, and then we can multiply the top and bottom again by root 3 over root 3. And then downstairs we're going to have a 3. Upstairs we're going to have a root 3. So root 3, that's equal to root 9, which simplifies down to just 3. Alright, so enough of the training wheels that are degrees. Let's switch over to radians. Okay, so let's go with part F here. Sine of 9 pi over 4. Okay, so first off, remember, when it comes to radians, the period of sine, cosine, cosecant, and secant are all 2 pi, which, depending on the denominator, is just going to be either 8/4 pi, or 6/3 pi, or something along those lines, or what else? Or 12/6 pi. So 9 pi over 4 minus 2 pi, which is in other words going to be 8 pi over 4. Multiply the top and bottom by 4 to convert it to fourths, is equal to just pi over 4. Now we can think about where that is. So this is pi over 2. Pi over 4 is halfway there, so it's that 45-degree angle. And that means the x and the y values are both medium. So they're not the biggest, they're not the smallest, they're the medium, which in this case means root 2 over 2, root 2 over 2. Alright, so then what does that mean? That means that the sine of 9 pi over 4 is the same as the sine of just regular pi over 4, which is equal to root 2 over 2. Alright, so now let's try the cosecant of 9 pi over 2. Or actually, let's just make it secant. This will be good for us. Secant of 9 pi over 2. So you'll find something interesting here, I think. So 9 pi over 2, we can subtract 2 pi, which is 4 pi over 2. 2 pi is always like double the denominator over the denominator times pi. So, okay, so that's going to be 5 pi over 2. Alright, well 5 pi over 2, again minus 2 pi. So it's going to be minus another 4 pi over 2. That's just going to leave pi over 2. Now let's think about that. Pi over 2, where is that? So pi over 2 is the same as 90 degrees, which puts us over here, which is 0 for x, 1 for y, which means that the secant of 9 pi over 2 is equal to, well, it's the same as the secant of just pi over 2, which is 1 over 0, which is undefined. So just as periodic values repeat their outputs, they also repeat the places where they fail to produce an output. So they are also periodic with respect to their undefined values. All right, H, and I think this can be pretty much the last one. Let's go with something worth our while. Cotangent, 17 pi over 4. All right, 17 pi over 4. Let's think about that. So cotangent 17 pi over 4. Well, we've been just subtracting 2 pi's before because we were talking about sine and secant and cosine and cosecant. But whenever we're talking about tangent or cotangent, it's multiples of pi. So let's just think about this. 17 pi over 4 minus just pi, which is the period of cotangent and tangent. So pi, which is the same as 4 pi over 4. So this is just equal to, so you just cut the numerator down by 4. So it's 13 pi over 4. Pi over 4 minus pi, it would be 9 pi over 4. And here we're really doing this in a very ungainly way. Anybody who wishes to try this in a more streamlined fashion could just figure out the multiple that we would subtract from the beginning and input that. But we're just going to use up the last bit of this sheet of paper here by continually subtracting pi. So 5 pi over 4, again minus pi, is equal to just pi over 4. So there we have it. That's the angle we're looking for, pi over 4. So where's that one? That's right here, which is going to be at root 2 over 2, root 2 over 2. And so the tangent, cotangent, I should say, of 17 pi over 4 is equal to the cotangent of just pi over 4, which is equal to root 2 over 2 over root 2 over 2, which is just equal to 1. Anything divided by itself, as long as it's not 0, just equals 1. And again, what we're talking about is the x over the y in the case of cotangent, which here the x and the y are the same. So you're dividing something into itself in the same way. All right. so that's the end of using the periodicity for this evaluation of trig functions. This is actually something we were already essentially doing in the last section. We just didn't, or actually in section 5.1 when we were placing points on the unit circle, we just weren't all that specific about what made the values equal each other. But now we're being specific about it, and it is the fact that the trigonometric functions are each periodic. Okay. Now let's talk about the signs of the trigonometric functions. That's sine as in positive versus negative. So in each quadrant, a different combination of the trigonometric functions will be positive slash negative, or negative. So let's think about this. So the order of the quadrants is this, and they cycle around in the order of standard position, so from 1 to 2 to 3 to 4. So these are the 4 quadrants. And here, let's just think about it first in terms of x and y. So quadrant 1, x is greater than 0, y is greater than 0. And what that means is all 6 of the trig functions are positive. All 6 trig functions are positive. All right, now in quadrant 2, what's the situation? Now the x is negative and the y is positive. And if we think about this, this means that all of the things that are specifically only involving the x will be negative. So, so what's that mean? So for one thing, cosine and secant, for one thing, are both negative. But also, if we have a positive divided by a negative, that'll always be negative. So that's going to be the case for tangent and also cotangent for the reciprocal reason. So cosecant, secant, tangent, cotangent are all negative, whereas sine and cosecant are positive. So what we have here is everything that does not, so everything that has any influence of the x in it is going to end up being negative. And anything that is totally absent the x, but only about the y, will be positive. Now down here, this is the quadrant where x is negative and y is also negative. And where that happens, we are talking about everything basically being negative except for the tangents. where negative over negative cancel out. So sine, cosine, cosecant, and secant, all negative. Tan and cotangent are positive. And again, it all just comes down to just the combinations of the x and the y. So I would not go around memorizing the specific list of which ones are positive or negative in each quadrant. I would always just try to think of it in terms of the x and the y. And then over here, what do we have? Now it's x that's positive, y that's negative. So what does this mean? This means all the ones that that involve the y are going to be negative, and all the ones that don't will be positive. So so let's look at the positive ones. So cosine and secant. Are positive. Sine, cosecant, tangent, cotangent, all are negative. All right, so now let's think about what this can do for us in terms of placing an angle in a quadrant from some information. So example, name the quadrant. All right. So name the quadrant, and so what we'll just have is some information, and we'll just have to piece it together. So let's say sine theta is less than 0, and let's say cosine theta is greater than 0. Now we have all this information like listed up there, but do we really expect ourselves to memorize those facts about all 6 functions? That's not really reasonable. What is reasonable is to think in terms of the x and the y. So this means y is negative, this means x is positive, and let's just think about how that can go. Negative y means below, means south of the equator here, and positive x means that it is east of the meridian. So that means we're over here. So the answer is quadrant 4. This is one way that these are often written, is just in the capital Roman numerals. Okay, well, what about this? Let's take another one. Let's say cosine is positive, tangent is positive. So now, what does that mean? So that means that x is greater than 0 and y over x is also greater than 0. Now, if y divided by x is positive and x also is positive, then could y ever be negative? No. No, because a negative divided by a positive is a negative. So that means that y has to also be greater than 0. So therefore y is greater than 0, which means that we're talking about positive x, positive y, so north of the equator and east of the meridian puts us over here, which is quadrant 1. Okay, well, I think you get the picture on that. Let's now move on to one of the more useful properties as far as connecting the trigonometric functions to each other. So the trigonometric functions are 6 different numbers associated with each angle. However, it turns out that using this property, we can get the other 5 essentially from just one of them. And these all come from the Pythagorean identities. And this is called the Pythagorean Identities because it's all based on the Pythagorean Theorem. So first off, here is the here's the original, the ancestral identity that connects all of them. So the Pythagorean identities essentially all come down to one fact that we can spin out in various combinations. Let's just think about it like this. Imagine we've got a circle, radius r, then the coordinates here will be x comma y. But what do coordinates mean? They mean that if we were to consider how far from the origin we go x steps in the horizontal direction and y steps in the vertical direction. And horizontal and vertical are at right angles to each other. So what that means is that x squared plus y squared is always equal to r squared. So this is the fundamental fact. And we've already seen this. And in fact, we'll see this over and over and over again. It is a recurring theme in this class. It is, more than anything else, the beating heart, in fact, of this class. So, consequences. So first, step 1, divide by r squared, by which I mean divide both sides of the equation by r squared. And what's that mean? So that means that we'll have x squared over r squared plus y squared over r squared is equal to r squared over r squared. Where does that leave us? Well, that's x over r. Whenever you're squaring a fraction, that's the same, or whenever you're squaring the top and bottom of a fraction, that's the same as squaring the whole fraction. Plus y over r squared is equal to 1. And then what does this mean? This means the cosine of theta, we'll call this angle theta, cosine of theta all squared plus the sine of theta all squared is equal to 1. And here's and for short, we usually write cosine squared theta for cosine theta squared and sine squared theta for sine theta squared. And we can reorder this equation to get the basic fun fact. So this is the takeaway. Sine squared theta plus cosine squared theta equals 1. So this is a memorable fact. Useful fact. Very useful. Okay, so that was consequence number 1, where we divided everything by r squared. Why did we do that? Because we wanted to make the kinds of trigonometric ratios that we were more familiar with. Now, we are also familiar with different combinations of x, y, and r. Those also make for different trigonometric combinations. So let's think about where that would go if we were to divide both sides by a different variable. Instead of r squared, maybe we can divide both sides by x squared. Divided by x squared. So what's that going to mean? It's going to mean x squared over x squared plus y squared over x squared is equal to r squared over x squared. Now what's that going to give us? Well, it's just going to be a 1 on the left there. Y over x squared is equal to r over x all squared. So 1 plus, now let's remember what's y over x, that's tangent. And over here, r over x, if it had been x over r, that's known to be cosine, so this is the reciprocal, which makes it secant. All right, so then this we can rewrite in the ways that are more familiar to see. So the way we would typically rewrite it is tan squared instead of tangent of theta squared. We typically write it as plus 1 in this order equals secant squared theta. Another useful fact. And this is just written in the way that you're most likely to see it out in the world. All right. So that's also a possible road that we could have taken with the x squared plus y squared equals r squared. But if we can divide by the x squared, why can't we divide by the y squared instead? So divide by y squared. So now we again take the x squared plus y squared equals r squared, and we'll go x squared over y squared plus y squared over y squared. So remember our original equation, x squared plus y squared equals r squared. So just give everybody here a denominator of y squared. And then over here we're going to have r squared over y squared. And then what's that going to make? Well, first off, we can rewrite it as x over y all squared plus 1 is equal to r over y, so that's going to be r over y all squared. Now x over y, that is the cotangent of theta squared plus 1 is equal to the just the secant. No, cosecant, what am I saying? Cosecant of theta all squared. And then the way that's usually written is cotangent squared theta plus 1 is cosecant squared theta. All right, so there we have it. Now, using these, using these facts. So here's the setup that we will be using, at least in this section of the book, as far as how to go about making any use of these. Given the value of one trig function and an extra bit of information. So given these, we will be finding. So find the values of the rest of the trig functions. All right, and the way we'll do this. So the basic idea is find convenient values for 2 of the pieces x, y, r, and use the Pythagorean to get the other value. Then use this to get the missing trig function values. All right, so let's start with it being super easy, actually. So we'll start with something where we have both the sine and the cosine given to us, just as a warm-up. So example, sine and cosine both given. And just see what we can do. Find the other four trig functions. All right, so first let's just start with something like this. Sine theta is equal to 4/5. Cosine theta is equal to -3/5. All right. So remember that sine equals equals y over r. Cosine equals x over r. So what we could do here is actually just go through the business of saying that x equals 4, r equals 5, y equals 4, just as I said. So sine is y over r. So y equals 4, r equals 5. And here, cosine. We can't ever make the r negative. So the x might be negative though, and x equals negative 3. So these would be some convenient values that we could choose. Well, if those are going to be our convenient values, then what we can do is then, so we have the sine, which is equal to y over r, which is equal to 4/5, and in fact was given to us. We have the cosine, which is equal to x over r, which is equal to negative 3/5, which in fact was given to us. And then we can have the tangent theta, which is equal to y over x, which we can then just write as 4 over negative 3, or negative 4/3. And then we can also do the cosecant, which are the reciprocals of all of the, so we can do the reciprocal functions now for each of these. So that's going to be 5 over 4. This one, the secant of theta, is going to be negative 5 over 3. And then the cotangent of theta is going to equal negative 3 over 4. So it's nice and easy when the sine and the cosine are both given to us most of the time. We may have to occasionally do something a little fancier, but what we can just do is find a convenient value for the r, the x, and the y, and usually what we'll just do is take the denominators of the fractions to be the r, and the numerators to be the y and the x. So as an example, let's just take something like this. We could do sine theta is equal to something like negative root 5 over 5, and cosine theta is equal to something like negative 2 root 5 over 5. So what we can do here is we can just cast the roles again, just like we did. We can just say that y is equal to the numerator, and so negative 5, r is equal to the denominator of 5, x is equal to the numerator of the cosine, which would be negative 2 root 5, and just whatever you do, make sure the r isn't negative. The radius being negative is pretty nonsensical. You may not go astray mathematically, but you'll be on pretty metaphysically shaky ground. So I would keep that straight. All right, so I'm just going to write them all, and just as out of habit, or to develop the habit, I will even write the ones that I have been given, just because they are part of the whole constellation here. So y over r is, y should be negative root 5. The negatives should always go with the numerators, so then that's going to be equal to negative root 5 over 5. Cosine theta is equal to x over r, which will be negative 2 root 5 over 5. And again, that was told to us, but it never hurts to recapitulate the known before branching out into the unknown. And then tangent of theta is equal to y over x, which is going to equal here, what is that, negative root 5 over negative 2 root 5. And this actually cancels. Root 5 over root 5, negative over negative. So what do we just get? We just get a 1 over 2. So the tangent actually cancels in a very clean way, because same over same always cancels in any fraction as long as it doesn't equal 0. Alright, now the reciprocal functions, cosecant theta, that's going to equal just the reciprocal of the previous result, so that's going to be 5 on the top and then negative root 5 on the bottom, which we can multiply the top and bottom by root 5. The negative can come out to the front, and what do we have on the bottom? We have, or on the top, we have 5 root 5 over root 25, which is just 5, which cancels, and that gives us just negative root 5. So the cosecant is just negative root 5. Secant theta will be, so it's going to be 5 over negative 2 root 5, which again, we will automatically start rationalizing the denominator here. And when you're rationalizing the denominator, you don't have to worry about any factors that are not currently irrational. So we just multiply the top and bottom by the root 5. So it's going to be, so the negative is going to come out to the front, and we're going to have 5 root 5 all divided by 2 times 2 times root 5, which is root 25, which comes to 5, which cancels, and we're going to have negative root 5 over 2. Alright, and then for the cotangent theta, this is just the reciprocal of tangent, which I can just use the most convenient form of the function over here to find that. And so it just will equal 2. So the way I recommend going about these, and this is slightly different from the advice that is given in the book and the advice that will be given on the homework portal when it gives you some helpful advice. This will be a little bit different from that, but it is the way that I think is the most straightforward for doing these types of problems. Now, a harder iteration of this is what we do when we are not given both the sine and cosine. Example, given only one trig value plus one extra piece of information. And here the tip will be use the one trig value to assign convenient values, and pick the values that would be most convenient for x, y, r, and use the Pythagorean Theorem to get the third. And when you are using the Pythagorean Theorem, you're talking about the square of something, and you're trying to take the square root of it. And so that means you're going to be put into a plus-minus situation and use the additional info. To decide between plus versus minus. So let's get started with something like this. So let's just say here's some information. So here. So let's just actually make that not an example, just a note. And then now the example. Find the remaining trig functions find the values of the remaining trig functions. So to start with, just to see what kind of thing we are in for here, let's just say that we have something like this. So cosine theta is equal to 5/13, and theta is in quadrant 4. All right, so that could be the kind of information that we might be given to work with. And what we do is take the information that's given to us and use it to assign convenient values to x, y, or r, and then proceed accordingly. So cosine theta is typically just x over r, which is equal to 5/13. So we might as well just say x equals 5, r equals 13. Now what's y? We don't know yet. We have to actually find that by using the Pythagorean theorem. So x squared plus y squared is equal to r squared. That's a fact for all time. And so we can just put in the values we know. So 5 squared plus the mystery y squared is equal to 13 squared. And you crunch the numbers and you find 25 plus the mystery y squared is equal to 169. You subtract 25 from both sides, and that means y squared is going to equal 144. Now, those of you who grew up studying the deluxe version of the times table, the one that went out to the 12s, to the 11s and 12s, will remember that this is 12 times 12. So if we take the square root of both sides, we'll get y is equal to 12, but because we took a square root of a square, we don't actually know, was y the positive or the negative version of this? Y squared equals 144. That's a fact that's true about 12, but it's also true about negative 12. So this is where we need to use this piece of information to make our decision. So quadrant 4 is down here. So y is going to be negative, which means we're interested in the negative version. So y equals negative 12. So as for the r, no matter what, we're never going to consider a negative value of r, just because the radius as a negative number doesn't really make any sense. But x and y certainly can be negative, and those will just determine which quadrant we find ourselves in. So x and y are both capable of being negative. R, on the other hand, can't. So now, let's just make our list of all the trig values based on this. So sine of theta. So that's equal to y over r, which would be negative 12 over 13. Cosine theta is equal to x over r, which this one was the one that was told to us, but it never hurts to confirm that it makes sense in the context of the numbers that we have been working with. So that's 5 over 13. Yep, checks out. All right, tangent of theta. So that's equal to y over x, which in this case would then mean negative 12 over 5. And again, when a fraction is negative, you can write that out front, and that would be the most common way of doing it. Cosecant theta. So that's equal to r over y, which would be 13 over negative 12, which again, most commonly, we would write the negative out front. Secant theta is r over x, which would be, again, just the reciprocal of the above, or in other words, 13 over 5. And then finally, cotangent of theta is going to be x over y, which is going to be negative 12, or sorry, negative, so the negative, again, we can just write out front of the whole thing. It's going to be 5 over 12. So it will be our habit when one of them is negative and the other is positive to just write the negative in front of the entire fraction. So that's the way this is going to generally proceed. So this was a relatively easier version of the problem, and now let's see what happens when the numbers don't work out so nicely. So 5, 13, and 12 are what are known as a Pythagorean triple. And what that means is, whenever you see that in a trigonometry problem, it's going to work out easily. But it won't be the case if you just use other numbers that you can expect them to be so nice. So let's try something with other numbers. So for example, maybe what we have is sine theta is equal to negative 2/3. And then maybe the information that we're given is that pi is less than theta, which in turn is less than 3 pi over 2. So in other words, theta is between pi and 3 pi over 2. So this is information that is supposed to help us deduce positive versus negative for whatever the missing value turns out to be. Okay, so let's just think about what we've been given and what it is in terms of y and x and r. So sine is equal to y over r, which is equal to negative 2 over 3. So then it makes sense for me to just say y equals negative 2, r equals 3. Now, if that's what I want to say, then x squared plus y squared always equals r squared. And what that would mean in this case is that mystery x squared plus negative 2 squared is equal to 3 squared. Now, negative 2 squared, the negative disappears, and what we get is x squared plus 4 equals 9. If I subtract 4 from both sides, I get x squared equals 5. Now that is not a perfect square. That's what's different here from the problem that came before, is that when I subtracted them, I did not get a perfect square, which means that if I take the square root of both sides, I'm going to get x is equal to positive or negative square root of 5. Now, is it the positive one? Is it the negative one? That's information that, as yet, I can't answer until I take into account the other piece of information that has been given to me. So the other piece of information is that theta is between pi and 3 pi over 2. Now remember, pi is 180 degrees, and then 3 pi over 2 would be an additional 90 degrees on top of that, so that puts us down there at the South Pole. So we're talking about quadrant 3, which means that x is going to be negative. X and y are both negative, but relevantly here, we know that x is negative. So we use this to deduce whether the x is positive or negative, and we deduce that it is negative. So x is equal to negative square root of 5. Okay, now when it comes to putting the pieces of this all into an answer, we just have to take them one at a time, start with the sine, which we already know, but it never hurts to just make sure. So negative 2 over 3, does that make sense? Yes. Now cosine theta. That's x over r, which is equal to negative root 5 over 3. Okay? And tangent theta is equal to, so that's y over x, which would be equal to negative 2 over negative root 5, which unfortunately, as you by now can tell, is going to need some cosmetic work here, namely a root 5 over a root 5 to rationalize the denominator, which then would lead us to, let's see, negative will cancel negative. We're going to have 2 root 5 over root 25, which is equal to just 5. Over here, where are we? So for the cosecant of theta, we have r over y, which is equal to, so negative 3 over 2, and again, we'll just write the negative in front whenever the fraction is going to be negative as an overall result. For the secant, what have we got? We've got r over x, which is going to equal 3 over root 5, and the whole thing is negative, so I'll just put that up front. But that is not rationalized, so I'll just carefully multiply the top and bottom by root 5. And that will give me negative 3 root 5 on the top. And then on the bottom, root 25, which just equals 5. And then finally we have cotangent theta, which is equal to x over y, which here would equal negative root 5 over negative 2, which would just be equal to root 5 over 2. The negatives will cancel, and that will be that. So that's what it looks like when you are not given both the sine and the cosine, but just one of the two. Now, by the same token, you could actually just be given a different one of the functions. So another option here for what we could be starting with would be something like this. So example C, let's just say what we've got is the secant of theta equals 3. So secant of theta equals 3, and we'll say furthermore that sine theta is less than 0. So those are the two pieces of information that we have been given, and we'll just try to figure out from this what we are talking about here. So let's just think about this. Whenever you have something that's just a number where you would have hoped it to be a fraction, you can just write it as a fraction by putting a 1 in the denominator. So secant of theta, which is equal to r over x, happens to equal here 3 over 1. So we might as well just say x equals 1, r equals 3. Now, as for the sine of theta, let's figure out what the y is first. So x squared plus y squared is equal to r squared, which means that 1 squared plus y squared is equal to 3 squared. So that means 1 plus y squared equals 9. Subtract 1 from both sides, y squared equals 8. So what that means is that y is equal to plus or minus square root of 8. And now we can use this piece of information to help us decide which it is, whether it's the positive or the negative. So if sine theta is less than 0, then that means we're talking about the y being less than 0, which means that we're not talking about the positive root 8, we're only talking about the negative one. Now when it comes to these square roots, we can simplify this. And the way you would simplify a square root of 8 is if the number that you're taking the square root of happens to contain any perfect square factors, then what you can do is factor them, and it would look like this. So square root of 8 is equal to square root of 4 times 2, which is equal to square root of 4 times square root of 2. But square root of 4, that's not a mystery. So remember, square roots, you can break those up into the square root of each of the factors. So whenever it's a multiplication or division, you can break the square root up in this fashion. And so square root of 4 is not a mystery, though. That's just equal to 2, root 2. So then this means this all equals negative 2, root 2. And it is customary to break these square roots down into the smallest factor that we can. Okay. So now, what does that leave us for the answer? So let's start with the sine theta. So sine theta is equal to, as usual, it's just y over r. So that's going to be negative 2 root 2 over 3. For cosine theta, that's equal to x over r. Now that's going to be here 1 over 3. And since cosine theta is the reciprocal of secant, that makes a whole lot of sense. And then finally tangent theta, which is equal to y over x, or you could think of it as being sine over cosine, whatever is most convenient. Here I choose the y over x formulation. So y over x, so that's going to be negative 2 root 2 divided by 1, which is just really negative 2 root 2, obviously. Dividing by 1 is not accomplishing anything. All right, now the reciprocal functions. So cosecant theta is going to be the reciprocal, so it's going to be r over y, which is going to be 3 over 2 root 2, negative in front of the whole thing, we'll just write, and then we multiply by square root of 2 over square root of 2 in order to rationalize the denominator. And what do we have? We have negative 3 root 2 over 2 times 2. So 2 times root 4, which is 2 times 2. Oops, sorry. And now that's going to be negative 3 root 2 over a total of 4. secant theta is r over x, which is just going to be 3 over 1, which is equals 3, which sure enough matches what we were originally given. So we haven't done anything that has contradicted what we started with. And cotangent theta is equal to x over y, which we can just then have 1 over negative 2 root 2, put the negative way out front, root 2, just to rationalize here, and that's going to give us a negative, and we're going to have a root 2 on top. We're going to have 2 times root 2, which is root 4, which is equal to 2. So we're going to have negative root 2 all over 4. So this is how you do it with a function such as secant. You just turn it once again back into its definition involving r and x and y, and then you can find all the missing pieces that way. Now, one last complication is when we are talking about specifically tangent or cotangent. So the last complication that can happen in these is that with tangent or cotangent, we might have to be a little bit careful about the negatives and positives. So, for example, D. Let's go cotangent theta is equal to 4/3. And we'll say furthermore that cosine theta is less than 0. So we have the cotangent given to us, and then we have to figure out what everything is from there. So first off, cotangent theta is equal to so that's x over y. So you might be tempted to just go straight away for x equals 4, y equals 3. That might seem very tempting. However, this would invalidate that. So what are we going to do here? So we need these to equal 4 over 3, but we can't actually have the 1 be 4 and the 1 be 3. The only way to do this, the only way to make this work is if we think about, I just want to do quadrants. So we think about the quadrants here. X is negative, so that means we are on the west side of the meridian, and the cotangent is positive, which means we can only be down here. So we're in quadrant 3. Now, if we're in quadrant 3, that means that x and y are both negative. So that means the only way to make this work is x equals negative 4, y equals negative 3. So the only way you can square the circle here and balance it out is to choose the positive versus negative values for the x and the y, essentially by relying on the information that's given to you about the quadrant, because cotangent and tangent involve ratios of x's and y's, so negatives cancel each other out, and so there's no way of telling if the numbers that you're given were originally both positive or both negative unless you had that other piece of information. And alternatively, if you have a negative value for the cotangent, then you have to consider, again, what quadrant you're in. So if x equals negative 4 and y equals negative 3, then what about the Pythagorean theorem? How is that going to play out? So x squared plus y squared equals r squared, fundamental fact, now and forever. So this is equal to negative 4 squared plus negative 3 squared, and that's equal to the mystery r squared. And if we square this, it's going to become positive 16, positive 9 equals r squared, 25 equals r squared, and so r equals plus or minus square root of 25, and we will always choose positive for r. No matter what quadrant you're in, the radius of the circle is always positive. So whenever you're solving for the r, always choose the positive one. So then that's equal to positive square root of 25, which is equal to just 5. So then that was the hard part, was finding the right x's and y's, but once we've got them, then everything will be easy. So sine theta, which is of course y over r, is going to just be negative 3 over 5. Cosine theta, which is x over r, will correspondingly be just negative 4 over 5. Tangent of theta, which is equal to y over x, will then just be negative 3 over negative 4, which is just equal to 3/4. And again, that's the kind of thing that we were counting on, was that negative would cancel negative, so we needed to juggle the positives and negatives to make it work out correctly here. And cosecant theta, so that's equal to r over y, which would be 5 over negative 3, and again we'll just write the negative in front in the usual fashion. Secant theta is equal to r over x, which will equal 5 over negative 4, so 5/4 with the negative in front of all that. And then finally, cotangent theta is equal to x over y, which is negative 4 over negative 3, which is then equal to 4/3. And now a quick reality check. That was the one that we were given to start with. And it all checks out. So that's how that goes. All right, so that is the Pythagorean identities as applied to these trigonometric functions, and really it all just comes down actually to the original Pythagorean theorem. This is nothing other than the traditional Pythagorean theorem, just dressed up in different clothing. Now, let's talk about the final topic of this section, which is even and odd functions. So even and odd functions. f of x is even if f of negative x equals f of x for all x. So what this means is you plug in a negative and nobody would even notice. It is totally insensitive to negatives. You plug in a negative and the negative just somehow gets canceled out, and it's as though it was never plugged in the first place. F of x is odd if f of negative x equals negative f of x for all x. So this is the exact opposite situation. Instead of the function totally ignoring the negative, this is a situation where you can pull the negative out to the front. So the reason why these are called even and odd is that these are the kinds of properties that even powers have and odd powers. So if f of x were x squared, this would be true. You plug in a negative into a square, and it's not so negative anymore. If you plug a positive into a square, it's the same as what the corresponding negative would have produced. And this is what is true of cubes, so they are odd. So now, if we think about the trigonometric functions, and we think about what it means to plug in even versus odd positive versus negative values, let's just think about the symmetries of the circle here. So in particular, so if theta is something like this, then what would be the case for negative theta? So first off, it would be down here. So this is negative theta. And let's think about what would happen to the x and y coordinates of it. So the x is still the same as it was. The y, though, will be the opposite of whatever it was. So when theta becomes negative theta, x stays the same, and y becomes negative y. So it becomes its opposite. So what that means is that all of the functions that are x specific are even, and all of the functions that involve the y will be odd. So the even functions among the trig functions will be, so these involve only x. So these would be cosine theta, and secant theta. Whereas all of the odd functions these are the ones that involve some amount of y. They involve y for sure, and then maybe x. So this would be sine theta, tangent theta, cosecant theta, and cotangent theta. So all four of those are odd functions. And based on this, so based on whether they are even or odd, we can either just disappear a negative from the inside of the function, or we can pull it out. So when evaluating a trig function, at an angle that's negative, we can either cancel the negative and that's for even functions, so for cosine and secant. Or or pull the negative out. And that's for odd functions. So as an example of this, let's just think about how this could be used. So example, use the even, odd properties to evaluate. So as an example here, let's just say we wanted to do something like this. So maybe cosine of negative 30 degrees. Now, at first, you might be thinking to yourself, I don't know anything about cosine of negative 30 degrees. If this had been cosine of 30 degrees, that would be fine. That's one that we've been looking at a lot. So what you can do here is you can use whether it is even or odd to either, first off, so to either cancel the negative, like make it disappear, or pull the negative out to the front. So cosine of negative 30 is equal to, well, cosine was the even one, so cosine and secant are the even of the trig functions, so that means that the negative might as well not even be there. So cosine is even. And that's then going to be the low angle here, so the x is what we're looking for, and this is the case where the x is the bigger value, root 3 over 2, and the y is 1/2. So that's equal to root 3 over 2. So if it's even, you can just completely ignore the negative. If it's odd, you can pull it out to the front. So let's try another one here. Let's try sine of negative 135 degrees. Again, it's easier first to just think in degrees and then work our way up to radians. So let's think about that. So first off, sine of negative 135. I don't want to think about negative angles. I just want to turn it into the sine of 135. Now, in order to do that, I just have to ask myself, is sine an even or an odd function? If it's even, the negative would just disappear. It might as well not even be there. If it's odd, however, then a different thing happens. And sine is an odd function, which means that the negative comes out to the very front. So sine is an odd function, which means that the negative will come out to the very front. So now the question is, what is the sine of 135? So here, let's think about that. So this is 90 degrees. So it's 90 plus an extra 45, so that puts us right here. And so the x value of this is negative root 2 over 2, and the y value is positive root 2 over 2. So this is going to equal negative root 2 over 2. So it's equal to negative sine of 135, but the sine of 135 is equal to root 2 over 2. And now let's do a couple in radians. So how about the sine of negative, actually, let's make it harder. Let's up the ante a little bit. How about cosecant of negative, what do I want here? Negative 3 pi over 2. So the cosecant of negative 3 pi over 2. All right, so first off, cosecant of negative 3 pi over 2. This has some relationship with cosecant of regular 3 pi over 2. So I just have to think about whether cosecant is even or odd, and then that will tell me if this is a negative or not. So cosecant is one of the odd ones because it's based on sine, and sine is definitely odd, which means then that the negative will survive. Now, if I think about what is the deal with 3 pi over 2, I don't even want to try to guess about negative 3 pi over 2, so this is 3 pi over 2. So that's going to be 0 for x, negative 1 for y, and that means that cosecant of 3 pi over 2 would just be 1 over negative 1, which is just negative 1. So this is equal to negative 1, which is just equal to 1. All right, let's just have one more, and then we'll call it good. How about the cotangent? The cotangent of negative pi over 3. All right, so first off, we have to ask ourselves what cotangent is. Is it is it odd or is it even? If it's odd, then this will be negative cotangent of pi over 3. If it's even, it will be positive cotangent. So cotangent is odd, which means that this is the same as just negative cotangent of regular pi over 3. Now we can ask ourselves about regular pi over 3. Pi over 3 is the same as 60 degrees. It's the higher one. So that's going to be the one with the x value of 1/2 and the y value of root 3 over 2, which means then cotangent of regular pi over 3 is going to equal y over x. Sorry, x over y, I mean, since it's the reciprocal tangent. So that's 1/2 over root 3 over 2, which is equal to 1 over root 3, which times root 3 is equal to just root 3 on top, and that's going to be root 9, or just 3 on the bottom. So cotangent pi over 3 is root 3 over 3. So this is going to be equal to negative root 3 over 3. And I said that was the last one, but we should probably do one more with the even functions because we've had mostly odd functions here. So one more here with an even function. Let's go with the secant of negative, let's go with 5 pi over 4. Secant of negative 5 pi over 4. All right. So first off, secant. Negative 5 pi over 4. We are going to try to relate this somehow to secant of regular 5 pi over 4. And the question is is secant an even or an odd function? Well, secant is reliant on the x, and the x doesn't care if the angle becomes negative. It stays the same x coordinate. So what that means is that it is even. So secant is even, which means that this is not negative secant 5 pi over 4. It's just equal to secant 5 pi over 4. Now, what is the secant of 5 pi over 4? So here we have a little bit more than pi, namely pi over 4 more than pi, which is going to put us down here. So 5 pi over 4, that would put us down here, which is negative, and it's root 2 over 2, root 2 over 2. So what that means is that the secant of 5 pi over 4 is equal to, so it's equal to, sorry, negative and negative, so they should both be negative. So it's equal to negative root 2 over 2, or 1 over root 2 over 2. And that's equal to negative 2 over root 2, so it's a reciprocal. That's another way of putting it. So we can or multiply both the top and the bottom by 2. And so now we just rationalize by multiplying by root 2, and we have negative 2 root 2 over 2, because that's going to be root 4, and those cancel, we get negative root 2 over 2. So that equals negative root 2 over 2. And the moral here is we never have to consider the negative angles basically at all if we choose not to. You can use the even or odd properties to always reduce the angle into something that is positive. If the angle is odd, then you would just pull the negative out to the very front of your answer and then proceed blithely along your way from there. If the function, on the other hand, is even, then what you would do is just ignore the negative, and it would be as though it were just regular, in this case 5 pi over 4, or in this case up here, regular 30 degrees. So it's as though we can just totally ignore the negative values for the angle and focus our minds only on the positive values, just keeping in mind the even or oddness of the functions in question. So this even and odd property, these are general function properties that you will observe, especially as you go into calculus. They will come up with some regularity. So make a note, even and odd. Even means the negative input disappears. Odd means that the negative input can be pulled out to the very front. Okay, well that's going to do it for this section, and I'll see you in the next episode of Math 112. Till then, bye.